All right, let's dive into something pretty fundamental today. Drift velocity. You ever think about how electricity seems to just flow instantly, like you flip a light switch and boom, light. Well, today we're going to find out why that's kind of an illusion.
Yeah, it's funny how our everyday experience with electricity can, I guess, sort of lead to a few assumptions that don't really line up with how electrons actually move.
Exactly. And to help us really break this down, we've got a really interesting interactive physics simulation and some text from Open Educational Resources and Open Source Physics at Singapore. They're designed for students, but honestly, the concepts here are pretty mind-bending for anyone, I think. So let's start with the simulation. Can you kind of walk us through what it actually shows us?
Sure. Imagine you're looking inside a wire, like on a microscopic level. What you would see is a field of atoms,
Hmm.
and they're arranged in this fixed lattice-like structure, like a really ordered crystal. And these atoms are vibrating just slightly because of their thermal energy.
So it's kind of like, I don't know, like a microscopic mosh pit with all these electrons just bouncing around off each other and off the atoms.
Yeah, that's actually a great way to think about it. It's pretty chaotic. Now, here's where things get interesting. The simulation, it lets you apply an electric field, kind of mimicking what happens when you actually connect a battery to a circuit.
Okay, so like when I'm flipping a switch.
Exactly. When you do that, the electric field, it creates a force. And that force acts on all those randomly moving electrons. It's like giving all of them a little nudge, all in the same direction. But it
Mhm.
doesn't stop them from moving randomly. They're still bouncing around. But now there's this slight bias, like a net movement in the direction of the field. And that's what we call drift velocity.
So it's not like they're all shooting off in a straight line.
Yeah, yeah.
It's more like they're still on that chaotic journey. But now they have like a favorite direction.
Exactly. And here's the thing about drift velocity. It's surprisingly slow, like really slow. We're talking millimeters per second.
Wait, hold on. If they're moving that slowly, how does my light turn on like in instant I flip the switch? Shouldn't it take some time for them to actually travel through the wire?
Right. And that's where things get a little tricky. You have to remember there's a difference between how the individual electrons are moving and how the electric field itself propagates. The electric field, the thing that's giving those electrons that little nudge, that travels super fast, close to the speed of light.
Ah, okay. So it's not like one electron is making the whole trip. It's more like a chain reaction.
Exactly. It's like that electric field is the messenger, and it tells all the electrons along the path to start drifting, all at basically the same time.
Okay, that makes a lot more sense. So drift velocity is this slow, well, kind of a methodical movement. What are some of the things that affect how fast or slow they drift? Like what affects the pace of that microscopic conga line?
Yeah, well, there are three main things: the strength of the electric field, the temperature, and the material of the conductor. So, starting with the electric field, a stronger field basically means there's a stronger force on those electrons, and that leads to faster drift velocity.
So it's like if you have a really enthusiastic conga line leader,
Yeah.
they're pushing everyone to move faster.
Yeah, exactly. Now, with temperature, it's the opposite. Higher temperatures mean the electrons have more thermal energy, so they're zipping around even more frantically. So they end up bumping into things more often, and that actually slows down their drift velocity.
Oh, I see. So it's like if you're trying to do the conga line in a really crowded room,
Yeah.
all those people bumping into you are going to make it harder to move in a straight line.
Yeah, that's a good analogy. Now, the last factor is the material of the conductor. Different materials have different electron densities, and their atomic structures are different too. So that affects how easily those electrons can actually move around.
So I guess it's like the difference between dancing on a smooth dance floor
Right.
versus trying to dance, in thick mud.
Exactly. Some materials are just better for electron flow.
So it sounds like drift velocity isn't just, some theoretical concept. It has like real world implications, right?
Absolutely. In fact, understanding drift velocity is really important in a lot of fields, like semiconductor technology, for instance.
Oh, interesting. So those tiny transistors that power like our phones and computers, they rely on drift velocity.
Yeah, definitely. By controlling the drift velocity of what we call charge carriers in materials like silicon, you can actually control the flow of those electrical signals. And that's basically how all modern electronics work.
Wow, that's incredible. So it's like
Yeah.
we're harnessing this really slow movement of electrons to create all this amazing technology.
Exactly. It's pretty amazing when you think about it. And it's not just microelectronics either. Drift velocity is important for things like electrical power transmission, too. When electricity is traveling through those long power lines, the drift velocity of those electrons, it actually contributes to energy loss because of resistance.
Oh, right. So the slower the drift, the more energy gets wasted.
Exactly. That's why power companies use those high voltage transmission lines.
Yeah.
Because if you increase the voltage, you can lower the current, and that helps to minimize those energy losses.
Okay, so even though drift velocity is slow, it still has a big impact on how efficient our power grid is.
Exactly.
It's amazing how something so small can have such big effects. I have a question, though. What happens if a wire breaks? Do the electrons, like, pile up at the end?
That's a great question. It really gets at the idea of what we mean by a complete circuit. For a current to flow, for those electrons to keep drifting, they need a continuous path. If there's a break in the wire, the electric field can't bridge that gap.
So it's like the conga line hits a wall and everyone just stops.
Exactly. You might get a little buildup of electrons right at the break. But without that complete path, that steady flow of charge, the current, it just stops.
Wow, this is making me think about all the wiring in my house differently. Like, there's this whole invisible world of electrons, but it only works if the circuit is complete.
Exactly. And that's just in, conductors like the copper wires in your walls. What about other materials, like semiconductors, or even liquids?
Oh, yeah, like salt water can conduct electricity, right? Does drift velocity apply there, too?
Well, the details might be different depending on the material, but the general idea, charged particles moving because of an electric field, that still applies. In metals, it's mostly electrons that are free to move. But in solutions like salt water, you have both positive and negative ions, and they can both move in response to an electric field.
So it's like instead of one conga line, now you have two going in opposite directions.
Yeah, that's a fun way to think about it. Positive ions are going towards the negative terminal, and negative ions are going towards the positive terminal, and all that movement, that's what makes up the electrical current in the solution.
So drift velocity isn't just about electrons. It's about any charged particle, depending on what material it's in. This whole deep dive is really making me realize that drift velocity isn't just some physics concept. It's like a key to understanding how the world works. From a light bulb to my smartphone, I'm seeing everyday things in a totally new way.
It really is, it's pretty remarkable how something like drift velocity can explain so much about the technology we use every day.
It is. You know, it's funny. We've been using this analogy of a conga line to picture drift velocity.
Yeah.
But imagine if we could actually see the electrons moving in the wires around us.
That would be something else.
Right. Would we be surprised by how slow they're moving? Or would it be, like, more amazing to see just how many of them there are,
Right.
all working together?
I think it'd be a little of both, honestly. Like, it's one thing to understand it in theory.
Yeah.
But to actually see it happening, it'd be, it'd be pretty awe-inspiring.
Yeah. It would definitely make you realize there's a lot more going on than we can see.
Yeah.
This whole deep dive has been like gaining a superpower. We can see these invisible forces that are all around us. And speaking of seeing,
Yeah.
for our listeners who are, maybe as fascinated by drift velocity as we are, we'll be sure to include a link to that interactive simulation we talked about. You can play around with it, change the electric field, the temperature, and really see how it all affects those electrons.
It's a great way to get a better feel for it all.
Exactly. Well, I think that about wraps up our drift velocity journey. But hey, the exploration doesn't stop here. There's a whole universe of, fascinating stuff out there just waiting to be discovered.
So stay curious and keep asking questions, and be sure to join us next time as we delve into another corner of the world.
Until then, keep those electrons drifting and those minds open. See you on the next deep dive.